So here we have instrumentation. You have the same program here, the same timeline, but for instrumentation, you prepare your code, you add some hooks into your code. So here you see this enter main, leave main, enter foo, and leave foo. These are calls that go into the measurement system. And there we collect interesting data, for example, the duration, the counts, maybe some hardware counters. But we do this at every function enter and every function exit. So this is a very detailed, or you get a very detailed representation of your program. This is an advantage. And disadvantage is that first you have to process your data before you do this kind of measurement. So because you need to insert the hooks. And if you have very small functions or very small regions, here, for example, the part where we come back from foo and then increase the loop counter and then enter foo again. So these, if the amount of work done in between these enter and leave functions is very small, then the relative overhead can be quite large. So, for example, if you use with a C++ application and you have lots of small inline functions, usually these are just some one-liners, then instrumenting every inline function usually causes a prohibitive amount of overhead. So you have to be careful here. Okay, now here we have all. We can measure the times here, and from the times we can do the durations of the functions. So how can you do the instrumentation, or when? So you can do this while you build your program. This is called the static instrumentation. So you provide some, for example, some compiler switches that insert at every function entry and function exit a call or a hook that then is processed by the measurement system. You can also insert some macros provided by the measurement system. You can do this by source-to-source translation before you compile your program. So there are different techniques, and different tools support different techniques, and it's also dependent on the compiler if one technique is better than the other. So, for example, if you use this automatic function instrumentation, some compilers disable inlining, which for a C++ program is pretty bad. Some compilers are pretty good at keeping the optimization high and just instrumenting the code after the inlining is done. So then there's dynamic instrumentation. This is, you have your unmodified program, and when you start the program, there can be some binary instrumentation, for example, some binary rewrite, or there's another technology from Intel called PIN, so where you start your program in some kind of virtual environment, and then you can do the instrumentation on the fly. As I already said, the code can be inserted manually or automatically. So manually, might be an advantage. So if you know your program well, you can just instrument the different phases of your program. You can instrument the initialization phase. You can instrument some important kernels, and you can keep this instrumentation always in, and you can then make easy comparisons when you change your program, and you see, okay, this with this change, just kernel X performs better or worse. So this is maybe a recommendation if you want to continually monitor your program with little overhead. Then manual instrumentation should be considered. Okay, and the automatic instrumentation can be done by a preprocessor or source-to-source translation tool, a compiler. You can do some link magic where you intercept, for example, some system functions like malloc or some other library functions, and which are then processed by the measurement system before the real function is called. And you can do this binary rewrite and this dynamic instrumentation. Okay, so what you need to keep in mind that with every technique you introduce some overhead, and you lower the performance of the program, and depending on the amount of instrumentation or amount of or the rate of events you need to process in the measurement system, the accuracy will decrease. It will also perturbs your program because the measurement system needs to allocate some own memory. So somehow it might push something out of the cache. So you need to keep this in mind, that the memory access patterns can be changed by using instrumentation or by using measurement in general. Okay. Well, and you always have to make a trade-off between the accuracy and the expressiveness. So if you just do some manual instrumentation of a few phases, then the overhead is negligible. But if you instrument every inline functions, then you have a totally different program, but you have a very correct representation of the program in at least in the way the function sequence, you're concerned with the function sequence. Okay, let's come to the second question. How is performance data recorded? So here we have these two options: profiling, runtime summarization, or tracing. So for profiling or runtime summarization, you just you will lose the time dimension. So you will just collect the total or the maximum of some metric. So for example, if you have a function foo that is called 3 times, first time with the duration of 1 second, second time with 2 seconds, and third time with 3 seconds. In total, you have 6 seconds. But so the time dimension that you have 3, and you also know that you have 3 calls, but you don't know the time for each individual call. So you can have some statistics. So, for example, some median and some quartiles, but the time dimension is lost. So same for the bytes transferred. So there you get a total, and also for the hardware counters and function calls. Okay, and you get these information for example, for functions, or if you manually instrument something for basic blocks or around loops, and you get data for processes and thread creation or thread management in general. So profile means a summarization of events over an execution interval. Yeah, so there are different kinds of profiles. You can have a flat profile, call path profile, and some special purpose profiles. So flat profile just shows the distributions of metrics per routine. So there's no calling context. So you just see that function foo is called 25 times, and that it took in summary 42 seconds, for example. In contrast, you have the call path profile, where you have usually a tree, and you see the you see the calling context. So you start with function main usually, and then you call function foo. From there, you call function bar, and you have the context. Sometimes the context is limited to 2 levels, because implementing this call path profile is more expensive than, for example, just using a flat profile, and using just 2 levels is a compromise. Okay, then you can also have some special purpose profiles that just focus on MPI calls or some OpenMP constructs. And then you can compare what's happening on different processes or different threads. Okay, so besides profiling, so we can have tracing as a means of collecting the data. So for tracing, the time dimension is preserved. So here you store information about some events, for example, function enter, function exit, during the execution, and you save then also a timestamp, and you also record on which location, on which thread, on which process this event took place, and also an event type, plus sometimes event-specific information. So if it's an MPI call, then you store the communicator, for example, or you sender and receiver, or bytes transferred. And you store these events chronologically, and then you get an abstract model of your program that you can, that you can replay to analyze your program. So for profiling, the time dimension is lost. You just get a summary. And for tracing, time dimension is preserved, and you get an abstract execution model of your program. Here is an example for tracing. So you have 2 processes. Process A has a function foo that sends something to process B, where it is received in function bar. So how would this look like in a trace? So first we need to do the instrumentation. So we have this enter and the exit of the function, and we have the send here with the event-specific information that it's sending to process B. And here in process B, we have the enter and exit of the function bar, and we have the receive with the event-specific information that it's receiving from process A. So when we monitor this program, we need to have some synchronized clocks. Otherwise, it's difficult to make some analysis, or it's nearly impossible to calculate some waiting times. So here's how a trace looks like. So we have local traces for each process. And here we have, in the first column, we have the time. So at time 58, we enter the function. Then at 62, we send something to B. And we exit at 64. And for trace B, we enter at 60, and we receive at 68. So 6 time units later, and then we exit at 69. So we can create a global view of this trace by merging the two traces together. So this is a conceptual merge. Nowadays, you don't merge it on disk because traces can be very large, and this is usually done by your trace reader. But this is in the end what you get and what you can then work with. So there are some advantages to do tracing. So you have this abstract execution model, and you can do all kinds of analysis you can think of, because everything is there. So the temporal and spatial relationships are preserved. This is a big advantage. And you can reconstruct this dynamic behavior. You can replay the trace and then, for example, calculate some waiting times and do some automatic analysis to find some bottlenecks. So, but there's a big disadvantage. So the traces can become extremely large. So, and they can become so large that you need to write something to disk during your application, which is what you want to prevent, because it causes lots of perturbation. So before you're doing a trace, usually you do a profile to find the interesting parts of your program, and then just trace the really important or the really significant parts to keep the memory amount handleable. Okay, so the last question here is, how is the performance data analyzed? So there are also two options. You can do it online, so during the program run, or post-mortem, so when your application measurement run is finished. So during online analysis, usually you work with some profile aggregation data, and you also sometimes use when you have MPI communication, you additionally send some extra information needed for online analysis, additional to the original MPIs. And here you also change the program behavior a little bit to get the information online. And quite often you have a hierarchical network of analysis agents that then collects the data, transports it to the top, and then does some analysis decisions. For example, you can then reconfigure the measurement run. For example, you start with a set of hardware counters, and at some point in time you analysis your program, and you see, okay, let's switch to a different set of hardware counters. Okay, but therefore you have to usually manually instrument your program to tell these analysis agents when they are due to do the analysis. Okay, post-mortem is what we do here during this workshop. So you store the performance data at the end of your measurement run, either as a profile or as traces. And then you can do some automatic detection of bottlenecks. You can look visually at the trace, and you can calculate lots of statistics. For example, here a trace visualization. So you have this a global trace we created a few slides before, and you can display it in two timelines, one timeline for process A, one timeline for process B. And here you have this function foo on process A, which started at 58 and ended at 64. And then you have function bar with its own start and end time. And then in between, you have this send and receive operation. You can draw an arrow, for example, to denote that process A sends something to process B. And this quite often gives you some direct insight about your communication patterns if the number of processes is reasonable and everything fits on your screen. Okay, so but you need to keep in mind that none of these options you cannot get the most of the analysis with just one option. Usually you have to combine different things, and for example, sometimes it's necessary to do sampling to reduce your overhead. Sometimes you can live just with some instrumentation. Profiling tracing can be used for different aspects. So, and usually you have to combine several tools or several techniques to, in the end, get what you want, a faster program. Okay. But before you start with the performance workflow we presented, so preparation, measurement run, analysis, and optimization, you should ask yourself if you have a problem at all. So you can make some scalability measurements to see if there's a scalability problem. Quite often there is one. You can also, for example, use some roofline models to see how do you perform on a specific machine. Are you near the optimum or not? So depending on your if your application is more memory bound or more compute bound. If you have a bottleneck, you need to find out what is the bottleneck. So is it more computation or more communication bottleneck? So is it an MPI, OpenMP? So therefore you can, for example, use a flat profile to quickly see where the problem is. When you want to see where the key bottleneck is, you can do some call path profiling, where you get the execution context. And then, if you also want to know why you have this bottleneck, and therefore you can use hardware counter analysis, for example, if it's a computational bottleneck, or you can just trace this part of the program to see if you have a communication bottleneck, which can be quite often analyzed with tracing. So, and also you want to know if your code has some scalability problems. So there you need to do some load imbalance analysis. So there you compare some profiles at various sizes, function by function. yeah, this is might be quite some time-consuming job to find this out where you have these scalability problems. Okay, and that's it for the introduction of terminology. So we now continue. Brian, we switch